Hello, everyone. Welcome to the online seminar on the mathematical foundations of data science. Thank you all for joining today. Our seminar is generously sponsored by 2 Sigma. It's my real honor to introduce our prestigious speaker today, Professor Benjamin Van Roy. Professor Van Roy is a professor at Stanford University, and beyond academia, he also leads a DeepMind research team in Mountain View. And he has also led research programs at startup companies such as Unica and Innovis. And he has also worked with Morgan Stanley. He has made fundamental contributions to the design, analysis, and application of reinforcement learning algorithms. He is a fellow of Informs and IEEE and has served on the editorial boards of Machine Learning, Mathematics of Operations Research, for which he co-edited the Learning Theory area, Operations Research, for which he edited the Financial Engineering area, and the Informs Journal on Optimization. He has received many academic accolades, including the MIT George Soros Doctoral Dissertation Award, the National Science Foundation Career Award, and the Stanford Tau Beta Pi Award for Excellence in Undergraduate Teaching and the Management Science and Engineering Department's Graduate Teaching Award. The title of his talk today is Simple Agent, Complex Environment, and Efficient Reinforcement Learning with Agent States. Without further ado, please join me in welcoming Professor Van Roy.
Oh, thank you for having me. And looks like it's a small group today, so we can actually have a good discussion. So feel free to interrupt and ask questions along the way. So this is joint work with Xi Dong and Zhengyun Zhao. This talk is about reinforcement learning. And the way I see it, the state of the art in reinforcement learning has really been driven by impressive results in simulated environments. And there's been a lot of effort in scaling up reinforcement learning agents to deal with increasingly complex environments. And the real challenge in reinforcement learning is to transfer this success over to real environments. And that transfer requires some major advances in data efficiency. This plot is meant to indicate that even for the simplest of robotics tasks, you have to train for perhaps a year or more to do anything reasonable with a robotic arm. Okay, so when you are working with a real environment, even to perform a simple task, the amount of training time required is onerous. And so we really require major advances in data efficiency to do useful things in real environments here. And ideally, these data requirements should be much smaller than the complexity associated with the environment. They shouldn't be driven by environment complexity, but it should be able to generate decent performance in a much smaller, over a much smaller time scale. And finally, when we look at the theory on data efficiency and reinforcement learning, in order for this theory to inform agent design and help us get to the point where we have data efficient agents, we really need to relax assumptions that are common to this literature. So here are a few assumptions that I think are critical to relax. So a lot of the literature assumes that the environment is a Markov decision process, and that's quite a rigid assumption that we want to relax. Okay, a lot of the literature further assumes that the environment is episodic, right, that it resets now and then, and that's an assumption that we need to relax to go to the real world. There's often assumptions embedded in results having to do with mixing times. Things like, the optimal policy in the environment mixes in some time scale. And again, in a real complex environment, that time scale is effectively infinite. So you don't want to be dependent on the mixing time of an optimal policy. And finally, a number of these agents in the theoretical literature assume that the lifetime of the agent is supplied as an input to the agent, right? That the agent knows exactly how long it's going to live for. And really, we'd like to design more flexible agents that operate in an endless way without a predefined time horizon. All right, so with that in mind, what is the formulation that relaxes those sorts of assumptions? It's one involving an agent-environment interface where at each time the agent executes an action and registers an observation, right? AT and then OT plus 1. And the cycle just continues forever. Okay, we're going to assume that the action set is finite and the observation set is finite. So these are the actions that the agent can execute and the observations that the agent can register through its sensors. Okay, so these actions and observations over time accumulate to form a history, A0 to OT. And an important aspect of this formulation is that there's a single stream of experience. Right? There's no episodes, there's no other complication that that impose requirements in the environment, but may simplify analysis. Here, we're just looking at a fully general interface for agent-environment interaction. All right, so here's an example, a dialogue system, right? You could imagine an agent that sends messages to an individual who might want help. Let's say the first message is, "How can I help you?" And the individual may spit back a message, and this process can continue. So in that case, the actions are messages and the observations are also messages, right? Or you can imagine an agent that is managing some kind of queuing network where the agent executes actions having to do with server assignments and makes observations in the form of queue lengths. Or you can imagine the environment being the internet, where at each time the agent's interfacing through a terminal, and the agent executes keystrokes and registers screenshots. Okay, so you can imagine an agent is having this endless interaction with the internet, right? Or perhaps the agent has a goal, like educating a population of people, and is seeing through its interaction on a terminal how well it's doing at that, right? And one thing common in these sorts of environments that become quite complex is the agent is going to be way simpler than the environment, right? The agent cannot be the same order of magnitude of complexity as the internet. All right, so you want to design agents in a way that even though the agent is much simpler than the environment, it can function reasonably.
So a question. So the environment you are considering is a POMDP or a MDP?
Neither. I don't want to make such restrictive assumptions.
Mm-hmm.
Okay. All right, so okay, so the agent design. Yeah, I'll tell you about the dynamics of the environment. Maybe that will answer your question, but I don't want to fixate on MDPs or POMDPs. The whole point of this is to get away from that. Okay, so agent design. All right, so we want to design an agent that operates effectively given an agent environment interface. Remember, an agent environment interface is a set of actions and a set of observations. That's it. Okay, we want the agent to be efficient across a broad range of environments and to be able to operate effectively when it's much less complex in the environment. So today's talk, along these lines, I'm going to present a simple agent that's designed for this regime. And the agent operates by tracking what I call an agent state. An agent state is what the agent maintains in its mind in order to select actions. It's sort of a simplifying lens. The agent doesn't want to maintain in its mind everything about the environment because that's too much. The agent state is just what the agent is maintaining in its mind. Okay, and the point here is that the agent can operate with limited memory and computation. Okay, and the particular agent I'm going to present is built on optimistic Q-learning, the optimistic Q-learning algorithm. And you might think that, how well does this agent perform? Well, part of this talk is going to be about studying the performance of this agent. And for starters, we can say that the eventual performance of this agent depends on how well aleatoric state can predict values. What's aleatoric state? So part of the agent state is what I call the aleatoric state, and I'll explain that further later. But the aleatoric state you could think of as features that the agent is using to predict value. Okay, and the eventual performance depends on how good those features are. And when we look at the data requirements to approach that eventual performance, that has nothing to do with how complex the environment is. Right? That only has to do with how complex the aleatoric state dynamics are. Okay, so we can sort of abstract away from the environment and think about the complexity of our features in measuring data requirements. Okay. So a few disclaimers here. I'm not recommending people use this agent. It's not a state-of-the-art agent. It doesn't have all the bells and whistles that make an agent state-of-the-art. This is really an agent that is meant to make it tractable for us to develop some theory that could then inform design of state-of-the-art agents. Okay, this is not a state-of-the-art agent in itself. Okay, and as we'll see, the agent can be improved in many ways, and it really serves as a constructive proof and a sanity check for some ideas. Okay, however, much of the theoretical RL literature works in this space that's completely disconnected from agent design, that just focuses on regret bounds for algorithms that would never influence agent design or are unlikely to influence agent design. So I do think that the particular agent and analysis we will talk about today actually has some intersection with real agent design, partly because optimistic Q-learning starts to look a little bit like elements of what go into practical state-of-the-art agents. Okay. And so because there's some overlap with actual agent design, hopefully this line of research offers a bridge between mathematical analysis and the area of agent design. All right. Okay, so I'll start by talking about the concepts that underlie this concept of agent state, reward, and policies. And then I'll move on to talk about performance of the agent through using those concepts. All right, so what's the agent state? The agent state, XT, is everything that the agent maintains in its mind. And if you look at state-of-the-art agents, they all have three components to agent state. Right? They don't say this, but if you try to think about what's going on there, you can factor their agent state into three parts. Right? There's an algorithmic state, which is just internal to the agent, has nothing to do with what it's acquired from the environment. For example, the algorithmic state can have to do with random numbers drawn in the process of executing the agent's algorithm. So, for example, if you're doing SGD or something like that, you're drawing random numbers, and sometimes some of this is retained as part of the algorithmic state. The aleatoric state is, you can think of as features. It's what the algorithm is trying to maintain and use to predict value. Right? And then there's an epistemic state, which is what the agent is using as its compressed representation of the environment. Like it could be a value function, it could be a model, it could be many different things. But there's some compressed representation of what the agent knows about the environment, and that's epistemic state. All right. Then there's, okay, so algorithmic state is the stuff unrelated to the environment. for our particular agent, the algorithmic state is going to be t, the time that the agent has lived so far. Okay, that's the only algorithmic state in our simple optimistic Q-learning agent. The aleatoric state in our optimistic Q-learning agent is going to be some notion of the agent's situation in the environment. Again, you can think of this as features that the agent's going to use to predict value. Okay, so in our agent, the aleatoric state is going to be updated by a fixed function supplied to the agent. So there's going to be some function that generates the next aleatoric state, st plus 1, as a function of the current aleatoric state, st, the action at, and the novel observation, ot plus 1. Okay, so finally, there's the epistemic state, which represents the agent's knowledge about the environment. Right? And then in our optimistic Q-learning agent, the epistemic state has two parts to it. One is a action value function, Q, which maps aleatoric states and actions to reals, right? This is a prediction of value. And the second part is a count function, which maps aleatoric state and actions to integers, okay? And so you can think of this Q-learning agent as being tabular, right? Keeps lookup tables over state action pairs, but the states are not environment states. The states are aleatoric states. All right, so here's how to think about what's going on with our agent. So the agent tracks aleatoric state, using this function f, the aleatoric state update function. So this is in the mind of the agent, right? The aleatoric state is not the environment state. It's just something that the agent is keeping track of to help it simplify how it thinks about its situation in the environment. And also the agent needs to decide whether or not it likes what it's seeing. And it does that through a reward function, little r. So little r, there is a reward function that maps the aleatoric state action and observation to a reward. Okay, so at each time step, the agent registers a reward rt plus 1, and it wants to make rewards high. Okay, so rewards depend on the history of interactions only through the aleatoric state. All right, so for each policy in this environment, we can define an average reward. Right? The average reward is defined in the usual way. Lambda pi is the limit of rewards averaged over time, capital T. All right, any questions? Okay. All right, so let's think about how this agent is applied. All right, so the way this works is you have the agent, and the agent requires some inputs at initialization. What are the inputs? One is the action set, another is the observation set, right? The agent needs to be told what are your actions and what observations can you register.
Professor Van Roy, it
Yes.
seems there is a question. So the question is from Romina Abachi, and the question is as follows. Could you please explain how your framework is different from the MDP and POMDP framework?
Okay, so let's go back to, okay, so in the MDP framework, right, there's the assumption is that the observation is the environment state. That's the effective assumption. Or more formally, right, the assumption is the next observation is conditionally independent of history, conditioned on the current observation and action. Okay, so that's a very rigid assumption. Now, POMDP is more general. Right? That allows the observation to depend on history in an arbitrary way if you define your environment state to be sufficiently complex. However, I don't see any good reason for thinking in terms of POMDP, because it doesn't seem helpful to me to think about what the environment state is when the environment state is infinitely complex, right? So you could think of what I'm doing as, using a model that could be served by POM-DPs, but where thinking in terms of POM-DPs is more encumbers more than helps you. Any other questions?
Yeah, maybe to follow up. So I was wondering how, when the agent is provided by the observation, does the agent know how to compute the aleatoric states, or is the agent is provided by the environment?
So this is what I'm beginning at right now. Okay, so let me just continue with this slide a little bit and come back to your question. Okay, so here's how what this particular agent is required. This particular agent requires in order to get started. Right, there's a set of actions, a set of observations, a set of aleatoric states. It's decided in advance. What is the set of aleatoric states? I mean, it could just be a set of indices, like a 1 through n, right? Aleatoric states. And then there's the aleatoric state update function, okay? So in our particular agent here, the agent requires the aleatoric state update function to be specified upfront. Okay, the agent is given the aleatoric state update function. And then the agent's given an initial aleatoric state. You have to initialize the aleatoric state. And finally, the agent is given a reward function, right, that maps state action observation triples to the unit interval. Okay, so those are the only inputs to the agent, no other hyperparameters or anything like that. Okay, so given these inputs, you let the agent loose. It just interacts with the environment indefinitely. Okay, does that answer your question?
Yes.
Okay, and I'll go through the exact algorithm later, but right now I'm just telling you what the inputs are to the algorithm. Yeah. All right, now at some level you could think of the agent as just a policy, right? The agent is applying a policy in this environment, and the policy selects actions by, you can assign a probability to each action, a condition on history. And because the agent state is only going to maintain the agent state xt, right? It doesn't use the rest of history. You can think of these action probabilities as depending on history only through agent state. So you can think of the policy as selecting an action AT given the agent state xt. Okay. The agent state is not aleatoric state. Agent state includes aleatoric state as part of it. Yeah. All right. So let me talk a bit about the algorithm the agent uses. I'm going to specify the algorithm precisely later, or more precisely later, but let me just talk at a high level what the algorithm is. Okay, the algorithm is optimistic Q-learning. And it's a tabular optimistic Q-learning, but tabular over aleatoric states, not environment states. And so we maintain an action value function and state action counts. And we just increase, and one issue here is, we're going to deal with the environment forever, and we don't really know how far ahead we have to plan in order to perform well, right? And so this version of optimistic Q-learning is going to be discounted. It's discounted Q-learning, but we're going to increase the discount factor over time, right? The other thing is, over time, we also have to nudge Q values to maintain optimism. Okay, that's typical of optimistic Q-learning. And I should mention, we build on some related work, but in this related work, the aleatoric state is taken to be environment state. Okay. One piece of related work that we really build on and borrow ideas from is a work by Jin and others on optimistic Q-learning, and their work had some similarity in spirit, but was really designed for episodic fixed horizon MDPs, right? And it took us about 2 years to go from that result to what we have here. So it was a lot of work, but yet, you know, it would have been a lot more work had Jin et al. Not produced that result. Okay, and contemporaneously with our work, there was work by Wei and others that focused on infinite horizon MDPs, no longer episodic fixed horizon. But that work, again, focuses on the case where aleatoric state is the same as environment state. And one thing I should mention is if you take our agent and an analysis and, you know, nudge it a little bit here and there, you can recover either of these results. Okay. So in a sense, our tools are a bit of a generalization to these works. All right, let's talk about performance of the agent now. So an important statistic we use in characterizing performance is a reward averaging time. Okay, so a policy is something that assigns action probabilities conditioned on history. Okay, so policy pi assigns a probability to each action A at each history H. And one thing is, for an agent to do anything useful, it has to be able to assess and compare policies, right? If the agent can't compare policies, it can't do anything useful. And averaging time is a statistic designed to allow us to bound the experience the agent requires in order to compare policies. Okay, so to define an averaging time, let me define a generalized notion of average reward, lambda pi HT. All right, lambda pi HT is the average reward averaged only over capital T time steps, starting at a particular history H. Okay, so it's averaged over a finite horizon, starting at a particular history. Okay, and the reward averaging time of a policy pi is the smallest time such that the difference between this finite time average reward over horizon capital T, starting at history H, and the long-term average reward lambda pi, okay, is less than or equal to the averaging time over capital T. Okay, so so it's a tau pi, the averaging time is a statistic that you know, it's minimal value that satisfies that inequality. Okay, and intuitively, it's sort of how much time it takes to get any sense of the value of policy pi. All right. Okay, so that's the averaging time concept. Another concept that's important to our framing and analysis is the concept of a reference class. A reference class is a class of policies, and our performance bound performance relative to particular reference classes. Okay, so let's talk about policy classes. Let P script be the class of all policies. Okay, so this is any mapping from history to action probabilities. And we define this restricted set, this policy class P script tau, to be the class of policies with reward averaging time less than or equal to tau. Okay, so it's the class of policies that you might be able to get some notion of evaluation of in time tau. Okay, so policies outside that class mean you definitely need more than time tau to assess their quality. And the way we frame our bounds is, you know, to capture the notion that the agent competes effectively with increasing reference classes. So in particular, you could imagine conceptually there's this horizontal axis, which is calendar time. How long has the agent lived? And then this vertical axis, which is what averaging times tau are such that policies with that averaging time, such that the agent can compete against policies with that averaging time. Okay, so over time, the agent can compete with policies that take longer to evaluate. Okay, and that makes sense. If a policy takes infinite time to evaluate, the agent's never going to be able to compete with it because the agent can't even figure out how good it is. Right? Even if you told the agent that policy, the agent could not figure out how good that policy is because it takes too long to evaluate. Okay, so the agent's competing with policies over time from growing classes where the class is constrained by how long it takes to evaluate those policies. All right. Okay, and the notion of performance bound we're going to pose is in terms of regret. So we'll assess performance in terms of regret. And, you know, for each tau, right, for each reward averaging time, we'll bound regret relative to p script tau. That's a reference class associated with that reward averaging time. All right, and the definition of regret is given here. It's the supremum over policies with that, you know, within that class, you know, which have at most that reward averaging time tau, supremum over the difference in the, you know, average reward for that policy and the realized reward realized by our agent. Okay. And, you know, our bounds also imply something about asymptotic performance. In particular, they imply something about this asymptotic performance with respect to the class of all policies. Okay, and you can think of that as a limb soup of the regret relative to all policies divided by t, which is equal to you know, the difference between the optimal average reward lambda star and the average reward lambda pi agent attained by our agent. Okay, so those are two quantities we'll bound. Actually, the first bound implies the second, but useful to think of these as two distinct concepts. Okay, there's going to be another statistic that appears in our bound, distortion. And the idea is distortion captures the loss in the agent's capabilities due to the particular form of the aleatoric state update function. Okay. All right, so first to define distortion, you know, we need some notation. We'll use, you know, we'll refer to the gamma discounted history action value function. Okay, so for any discount factor gamma, we have a optimal value function q star gamma, right? And our agent is going to be predicting value, not using history, but using aleatoric state. Okay, so you can think of aleatoric state as a function phi of history because, you know, the aleatoric state was computed using all the observations to date. And so all the observations are in history. And so the aleatoric state is a function of history, a function phi of history. Okay, so the aleatoric state at any time is a function of history. And the distortion delta tau, we'll call this the distortion over effective planning horizon tau, is the maximum over state action pairs of the largest minus the smallest optimal value across histories that correspond to that aleatoric state. Okay, so it's sort of like how much can value vary if I only know my aleatoric state. Okay, if I know my aleatoric state, I can't predict value exactly because I don't know the history. And so the question is, what is the possible variation in value if I knew the aleatoric state? All right, and in this expression, the discount factor gamma is 1 minus 1 over tau. So, you know, there's this relation between the effective planning horizon tau and the discount factor. The effective planning horizon tau can be thought of as 1 over 1 minus gamma. So gamma can be thought of as 1 minus 1 over tau. Right. All right, one last concept we'll need is the worst case over horizons greater than or equal to tau. Okay, so delta bar tau is just a supremum over tau prime greater than or equal to tau of delta tau prime. Okay, so this is the worst case distortion over planning horizons larger than tau. Questions? All right, so let me share the regret bound now that I can state using these statistics. Okay, so here's the regret bound. So the regret relative to reference class p tau at time capital T is going to have 3 terms to it. The first is a persistent term. Right? This scales linearly with capital T. That's why I call it persistent. It never washes away with time. Okay, and that's scaled by delta bar tau. Okay, so this is inevitable because the agent cannot predict value exactly using its aleatoric state, and delta bar tau is trying to measure that distortion in value predictions. Okay, and so there's that term that scales with that inevitable error. All right, the second term is transient. Right, it grows at a rate smaller than capital T. Right, and in this particular case, the rate is t to the 4/5. Right, and in there is a square root of state times actions as well. Right. And finally, there's a term that's dominated. So I don't worry much about the third term because it becomes insignificant relative to the other terms pretty quickly. Okay, so a few remarks. One is an interesting aspect of this result is that there's no dependence on the number of environment states. Okay, the number of environment states could be infinite, right? Has nothing to do with this result. And there's no dependence on any notion of mixing time in the environment, right? There's no notion that some policy has to mix quickly in the environment. Nothing like that in this bound. The other thing is, it takes some mental gymnastics to get here, but if you think through this bound carefully, one implication is that it's suggesting that at time capital T, the agent can plan effectively over horizon tau, or effective horizon tau. Okay, so at any time, the agent is sort of making good decisions in the sense that it's planning over horizon that's the 5th root of how long it's lived. Okay, so when the agent starts, it can't plan very far ahead very well, but as time progresses, it plans further and further into the future. Another important thing to note is that, much stronger results can be proved using the same analytic tools, right? If the agent is given a fixed lifetime tau, the agent's given t, if the agent's given t as input, right? And or the agent's given a horizon tau as input. If the agent's told, hey, to do well in this environment, you really only have to plan over horizon tau, right? Because the environment's episodic, for example, right? Then you can tweak the agent and tweak the analysis and the bound looks way better. Okay, so some of the aspects of this bound are really driven by the fact that the agent is not privy to such knowledge about the environment. All right, and there's also an asymptotic performance bound that's implied by that regret bound. So to think about the asymptotic performance bound, let's define another policy class, P tilde. P tilde is a class of policies that select actions based on history only through aleatoric state. Okay, so actions depend on history only through aleatoric state. Okay, that's a class of policies. Okay, and let pi tilde be the best among those policies, the one that maximizes the average reward among those policies. Okay, so you can prove an asymptotic performance bound based on, it's a corollary to our regret bound that says the difference between the optimal average reward. This is optimal among all policies, that these infinitely complex policies that could depend on environment state. Okay, lambda star is the best possible policy in the environment. Okay, so that asymptotic performance bound says the difference between the optimal average reward and the average reward realized by the agent is bounded above by 4 times this measure of distortion. Well, again, the measure of distortion needs a horizon. The horizon is tau pi tilde. That's the reward averaging time of the policy pi tilde. Okay, so the best policy that makes decisions based on aleatoric state requires time on the scale of tau pi tilde to evaluate, right? Okay, so we look at distortion at that scale and above, and can use that to bound this difference in average reward. Okay, one thing I want to mention is this, resolves an open issue that's been lingering in my mind for many years, that I wrote about in a 2006 paper. And that is that, for a number of approximate dynamic programming algorithms, you can show that the difference you can attain in these in lambda star minus the average reward given by the approximate dynamic programming algorithm is bounded below by this distortion times the reward averaging time. Okay, and so it looks much worse, right? Because the distortion gets scaled by the reward averaging time, right? And this is a lower bound that holds for a number of approximate dynamic programming algorithms, right? And approximate dynamic programming algorithms are different from reinforcement learning algorithms in that they have access to the environment model, right? They can query transition probabilities, they can simulate, they can do whatever they want. Okay, but there are a number of approximate dynamic programming algorithms that for which you have this lower bound. Now, there's a particular characterization of an approximate value function that I call the TD fixed point. It's a fixed point of temporal difference learning. Q-learning is a form of temporal difference learning. But there's something called a TD fixed point, which you can show attains this upper bound, right? So it doesn't involve that scaling by tau pi tilde. It doesn't involve a scaling by the averaging time. Okay. However, I never knew how to compute that fixed point or how to attain how to get a result, an algorithm that attains such a bound. Okay, so in a way, this regret bound closes this issue in my mind within a factor of 4 at least, because now we have an algorithm that gets that level of average reward. Okay. All right, let me dive into more detail on the agent. So here is the algorithm. Here is the version of optimistic Q-learning that we analyzed to get that regret bound. Okay, so how does it work? Well, we start by initializing the aleatoric state. Right? The inputs are the initial aleatoric state, the aleatoric state update function, and the reward function. Okay, those are the inputs. I suppress the notion that the action set and observation set are inputs as well, but I think that the agent needs to know what the actions and observations are. Okay. Okay, so you initialize the aleatoric state, and then you initialize action values and counts. Okay, Q and M. And then you set an effective planning horizon. Now, foo1t is a subroutine here. It's a fixed function of t, right? So for each value of t, there's a number, foo1t. I didn't write down the expression here because I didn't want to make this too cluttered. But just think there's some fixed sequence, foo1t, here, subroutine. And then you set the optimism coefficient using foo2t. And then you inject some optimism to all action values, for all state action pairs. And the idea here is because you're increasing the horizon, you need to become more optimistic everywhere because you're increasing the horizon. And so more good things can happen further into the future that you didn't account for before. Okay, so you need to increase all these values. And finally, you reduce the counts a little bit, or either a lot occasionally or a little bit at a time, in order to reduce emphasis on old data, right? Because the old data was sort of, when you were trying to learn with a smaller discount factor. And so you need to sort of forget about that as the discount factor gets much bigger. Okay, and then you select a greedy action with respect to the action value function. And then you increment the count. You say, I just saw the state action. Oh, you execute that action and you register the observation. Okay, then you increment the count for the state action pair. Like I just saw that state and that action. So increment the count. You choose a step size. Okay, that's the step size formula. Depends on the count in the horizon. And then you update the aleatoric state using the aleatoric state update function. And then you convert the effective planning horizon to a discount factor. Okay, that's this mapping. There's an association we have between discount rate and effective planning horizon. Okay, and then you do the typical optimistic Q-learning update. Okay, there's a discount factor gamma in that update because this is discounted optimistic Q-learning. Whoops, and that's it. Okay, so any questions?
So there's a question in the Q&A in the chat board, which is about the definition of distortion. So why is it called distortion? Is it something that we want to relate to the rate distortion theory?
That's a good point. You could do a rate distortion analysis here. You could. But more broadly, it's the distortion in the sense that it is the extent to which our compression of history hurts our ability to predict value. Right? Aleatoric state is a compression of history. Right? So, it distorts our aleatoric to predict value. Yeah.
So does that mean, say, the space of the aleatoric space, the aleatoric state is misspecified, then we will sacrifice some distortion factor?
You could think of distortion as a measure of misspecification, sure. The distortion itself could be thought of as a measure of misspecification. It's a measure of the loss due to the quantization.
Thank you. And as for the optimistic Q-learning algorithm, is it possible to incorporate function approximation in the?
Yeah, I'll mention that toward the end because I think that's an important topic, and we haven't done that yet, but I think that's an important topic. All right. Okay, so that's pretty much it for what I wanted to talk about, but I wanted to leave with you some open issues that I think this community could contribute a lot to. Okay, so first of all, it still lingers on my mind whether this performance bound can be improved, and I suspect you can reduce this to a factor of 2, but that remains an open issue. Next, you got to admit this regret bound is loose, right? And the agent is not particularly well defined. It's a pretty naive, optimistic Q-learning agent. And there are lots of practical tricks in reinforcement learning that might improve this agent as well as the bound. And one, for example, eligibility traces might be brought into the picture, right? And there's this relation we have implied by the bound of, if you have lived for a time capital T, you can plan well over time capital T to the 5th root, right? I suspect that planning horizon can be extended a lot, maybe 4th root or 3rd root or something, if you bring something like eligibility traces into the picture. Okay. And then, there's randomized exploration schemes, which I think for this kind of an agent could actually work significantly better than just injecting optimism in the temporal difference update. And then there's the question you just asked about, which has to do with going beyond tabular representations. And so I think this is a very important open area. How can we generalize across aleatoric states? And beyond that, rather than having a fixed aleatoric state update function, how do we adapt that function over time in order to improve our state representation? And if you look like at a state-of-the-art agent like mu0, for example, it's doing both of these things. So it's adapting an aleatoric state update function over time, and it's generalizing over aleatoric states in order to predict value. And it uses neural nets in both cases. Okay, and then beyond this particular line of research having to do with these sorts of regret bounds, I think there's a lot of many directions in this general area of developing theory for this broader model of agent-environment interactions in a way that could inform real agent design. And one thing I find really promising is the information theoretic approach. And we talk about that a lot in this recent paper, Reinforcement Learning Bit by Bit. But I think that those sorts of tools, if developed by a mathematically strong community, could overtake the tools we're using right now and could really inform agent design in a more practical way. Then there are concepts of going beyond learning from rewards. If you look at an algorithm like Q-learning, right, it's sort of silly in a sense, because when you look at the update of epistemic state, it's based on a temporal difference that only uses reward feedback. Okay, there's so much other feedback coming in through observations, and none of that is being used in the updates. And so it's kind of silly. If you want to design a data efficient agent, you should be using all the data. You shouldn't just be using rewards to learn. Okay, so there's a big open area here is how to leverage the rest of these observations. And then there's this issue of tracking. The spirit of this optimistic Q-learning algorithm I gave is sort of you're trying to converge on something. Implicitly, you're trying to converge on a policy that's really good among those that can be represented as functions of aleatoric state. But actually, if you're really going to live for a long time, you might not want to converge, right? You might want to track, because you might find yourself in very different situations in the environment over time, and you don't want to ossify around a particular way of dealing with the environment. Okay, so you might be able to come up with better regret bounds by designing agents that don't converge. And finally, are agents based on a discounted Q-learning concept? An open question is whether you can do better working directly with an average Q-learning concept. Okay, okay, so that's it. Thank you. And as you can see, there's so much to do here, and so many issues that can benefit from strong mathematically minded researchers who can shape this area, who will do careful and thoughtful work to elucidate some of these issues. Thank you.
Thank you, Professor Van Roy. So maybe due to the time limit, maybe just let's look at a few questions. And the first question is, I was wondering whether it's possible to derive an average case analysis, say a Bayesian regret. And also, is it possible to conduct a problem-dependent regret bound?
Well, first of all, okay, good. So the result I presented is of the frequentist variety. And it implies a Bayesian regret bound, right? Because for any prior probabilities, you can average the right-hand side of the bound. So that implies a Bayesian regret bound. Now, in a sense, that bound is also problem-specific, instance-specific. It depends on the instance through these statistics having to do with like delta, for example, the distortion, right? And the reward averaging time, sort of comes into play in defining the reference class, right? So you can consider those related to instance-specific concepts. Now, maybe you want to bring in more information about the environment into the bound, more statistics, right? Make it more specific to instances, but it already has some elements that are instance-specific.
Mm-hmm. Well, if we have some something like a gap, then is it possible to bring the polynomial dependency on T to logarithmic dependence?
Yeah, that's easy to do, but I think that's not useful to do because the gaps, if you look at, suppose you take a gap for the, between the best and second best option action in the environment. Right? If you have an infinite number of states, the gap's going to be 0. So that's not very informative. Now, even if your gaps depend instead on some notion of aleatoric state, even then, there's going to be so many aleatoric states that the gap's going to be very small. So I feel like going down that line of analysis is just the wrong road.
Thank you. And another question is regarding on the updating rule for the aleatoric state. I was wondering, is it possible to also learn this function?
I think that, for a practical agent, it's got to be the case that you adapt that function, right? And as I mentioned, mu0 does exactly that. It adapts the aleatoric state update function. However, developing theory that guides that is a big open area, as I mentioned.
Thank you. And I think the time is almost there, and maybe we can just stop here. And thank you again for your time.
Thank you very much.
Thank you. And also, we would like to thank the audience for attending and look forward to seeing you next week. Thank you.